Hi everyone. Today we're going to be finding the volumes of 3D figures, which we've actually been working on for a little bit, but now the way we generate that figure is a little bit different. So like you saw in class today, what we're going to be doing is taking curves, or the area bounded by certain curves, and revolving that region around some axis. And so what we found out today is when we do this, all of our cross sections are going to be circles. So that's going to give us a nice way to find the volume using integrals. So let's take a look at how this works to actually find these volumes. So like we just said, sometimes we can find the volume of a three-dimensional shape by taking a curve and rotating it around a given axis. Now, I want to make a note here. This could be the x or y axis, but really in more general terms, the axis could be any horizontal or vertical line. And so we'll kind of tuck that away. We'll see problems like that, probably not in this video, but when we're back in class. So just keep that in mind. Axis really means any horizontal or vertical line. Okay, and so when we do this, when we revolve or rotate that curve around an axis, we know that if we were to cut through that, each of the slices would be a circle. So, to compute the volume of the 3D figure that's created when we revolve around a given axis of rotation, this is what we're going to do with our integral, right? So we already said the slices were going to be a circle. So in this case, we're adding up the areas of circles, and we know that our area is pi r squared. Now, like when we did cross sections, we're going to be using our integral to add up the area of all these circles. The nice thing here is the only area formula we're going to need is the area of a circle. Now, what we need to do here is realize our area is pi r squared. Now that area is going to be defined by our region here. So when I look at this, so in our example, our shaded area here is the area that we're going to revolve. Now, these cross sections are going to be circles, and the radius, this is probably hard to see, the radius is really going to be the distance between the top of that curve and the bottom boundary here. I should say the top boundary and the bottom boundary. So that region, the radius of that region, is going to be defined either in terms of x or y, depending on what you're revolving around. So what we're going to do is we're going to have an integral. We're going to have pi times the integral from a to b. So if I were looking at this, in this case, this would be a and this would be b. Now, I'm going to have my radius in terms of x. Again, that's going to be determined by our function. We're going to square that radius and then finish off with the dx. I want us to be really careful with notation here. A lot of people are starting to drop that dx, which is something we can't do. Now, I'm going to make a note. This is if we're revolving around the x-axis, which is what's happening in this picture. Now we'll see as we go around, or as we go along doing problems, we could also revolve around the y-axis. And in that case then, our volume would be pi times the integral from a to b. Now our radius would be determined or defined in terms of y. That radius would be squared, and we would have a dy. Okay? Again, the idea is that pi r squared is the area of our circle, and we're using that integral to add up all the circles that occur between the bounds of a and b to generate that solid. Now, we call this the disks method. We won't refer to this a lot, but in case I use it, I want you to know what I mean. So disks are generated when I revolve and I have a solid figure. There's no holes in it. What happens down here is a little bit different. Now I'm looking at a region that's bounded between two different curves. You can see the top is g of x, the bottom is f of x, And in this picture, I'm revolving about the x-axis. What you'll see here is there's all this empty space in between my region and the x-axis, and that's going to create a hole in my solid. So you can kind of see here, if you imagine this hole in the center that's carved out through that solid. So when that happens, we call these washer problems, when there's that hole in the center. And again, that's created because between my region here and the axis about which it's being revolved, there's some negative space. You can see here, if I had highlighted up above in red, there's no space between that shading and my x-axis. So that's why we didn't have a hole here. So now this is going to look a little different. When there's a hole, there's some volume that we have to subtract out. So what's going to happen is, what I really have, I have kind of two radii. From my very top curve to the axis, I'm going to call that big R. I'm sure that's very hard to see, but that's called big R. And then I'm going to define my little r between the lower curve and that axis. And so now we're going to have to subtract. I'm going to take pi times the integral from a to b. Now I've got my r of x, that's my radius, and I'm going to square that, dx. And then I have to subtract out this smaller volume, subtract out the hole in my figure. So pi from a to b, here I called this little r of x. I still square that, and I have dx. So essentially we're doing what we did above, but we have to do it 2 times to account for that area, or that volume, excuse me. Now, you'll see a lot of times I don't write this out as 2 separate integrals. I factor out that pi, and I just make it the integral from a to b of r of x squared minus my little r of x squared dx. Now, I just showed this in terms of x. Obviously, if we're revolving with respect to y, or around the y-axis, we would need to change our variables. The other thing I want to point out is when you have your radii, make sure you square them individually. Otherwise, you're going to get that problem wrong. So, let's take a look at some problems. We're only going to do 3 of them. I think that'll be enough, and then we'll go through the others in class. So, let's take a look at the first one. Okay, so it says to find the volume of the solid of revolution generated when y equals negative x squared plus 4. So you can see that's graphed for us here. And the x-axis over the interval from -1 to 1. So let's first make sure we know what region we have. It was this curve and the x-axis, but I'm only going from -1 to 1. So I'm talking about all this area in between here. That's what I'm going to revolve. Okay, and now I'm revolving that around the x-axis. So here's what I'm going to do. I like to highlight, when it says revolved around the x-axis, I just like to draw that in red. And what that does for me is shows me that there's no space in between my shaded region and my axis. So I know this is going to be a disk. There's no hole that I have to worry about. Now, my radius, I know, is going to go from the top here all the way down to where I'm revolving. Again, I only have one radius because there's no hole. So my top is this function here. I know that blends in. And my bottom is what's in red. So my area function, because they're always circles, is pi r squared. Now my radius, since I'm going around the x-axis, I'm going to have everything in terms of x. So my radius is just the distance between the top and the bottom function. Now in this case, my top is negative x squared plus 4. The bottom is just the x-axis, or y equals 0. So my radius is negative x squared plus 4. Again, just the distance between the top and the bottom. So now I've got my radius, and now I can use my volume, again, to add up these areas. So my volume is, I like to pull the pi out because it's constant. I'm integrating, since it was just from the interval from -1 to 1. Those are my bounds. Now I need my radius squared, and we said our radius was negative x squared plus 4, and then I have my dx. That's everything for my setup. And again, I'm going to start being really picky to make sure we have that dx in our notation. So make sure you're not leaving that out. So now, for our purposes, we're just going to go ahead and use our calculator to calculate this. So I'm going to put it in my calculator. I recommend you do the same. And trying it out is going to be really important too, to make sure you get your parentheses right. When I do that, I get a value of 85.032. And I always go to the thousandth to 3 decimal places because that's what the exam does as well. Okay, so that's one basic example, just revolving around the x-axis. So let's look at number 2. Okay. For number 2, it's asking me to find the volume of the solid of revolution generated when x equals negative y squared plus 1, which has already been graphed for us here. Let's see, and the the y-axis between y equals 0 and y equals 1 is rotated about the y-axis. So a few things here. Let's get our region. We know it's bounded by this curve between, let's see, it's bounded by the y-axis, and I'm going between, let's see, y equals 0 and y equals 1. So from 0 to 1 is just this piece here, right? We don't want to go here because it's saying it's between y equals 0 and y equals 1. So that's the region that we're going to rotate, right? And now it said we're rotating around the y-axis. So now I've got my region. I'm going to highlight that axis. And again, you can see there's no gap in between there. So this is going to be another discs problem. I only need one radius. And my radius, in this case, is going to be right minus left because we're going about the y-axis. So let's see what that would be. My right boundary here is my function negative y squared plus 1. My left boundary is just right here, x equals 0. So I get negative y squared plus 1 for my radius. So now my volume, I have to have pi, because that's my pi r squared. My values, again, since I'm going with respect to y, have to be y values, so that's from 0 to 1. I'm going to have my radius squared, and this is going to be dy. And we just found our radius is negative y squared plus 1. Now, this says no calculator. We're going to have to work this out by hand. So the first thing I'm going to do before I try to anti-differentiate is just expand this out. So I know I'm going to have negative y squared squared, which is going to give me y to the 4th. I'm going to have minus 2y squared for my middle term, and then plus 1 dy. So now we can go ahead and anti-differentiate. So I'm going to have pi times y to the 5th over 5 minus 2/3 y cubed plus y plus c, and I'm going between 0 and 1. So now I'm going to plug in. I have 1/5 minus 2/3 plus 1. Now I would have a plus c. When I plug in 0, though, everything's going to cancel as well as that c. So I'm kind of done here. So let's make a common denominator. Looks like 15. So 3/15 minus 10/15 plus 15 over 15. So I get a negative 7 plus 15. Looks like 8 pi over 15 is our answer for that. Now, just so we're kind of revisiting what these things are going to look like, if I took this little bit here, kind of looks like this. When I'm revolving it, essentially what's happening is I'm getting something that looks like this, if you can kind of picture that. And it has all these circular cross sections. And again, that's what we're doing when we're taking this integral, is just adding up all the circles that make up this three-dimensional solid. All right, we're going to skip 3. We'll do that tomorrow. And we're going to look at number 4, because now something a little bit different starts to happen. Let me move this up. Okay, so now we're going to find the volume of the solid of revolution formed by rotating the region bounded by these two graphs. We're going to rotate that about the x-axis. So now I can see this region that's being bounded here is this right here. So that's the region that's going to be revolved. Now, if I can kind of draw this, I kind of have this petal shape here. And if I kind of reflected it, I get something like this. And so now I'm going to have kind of these outer circles, but I'm going to be taking away these inner circles here. I don't know if that helps, but to kind of maybe visualize what's going on here. I'm going to have a hole in the middle of that solid, because if I go about the x-axis, right, you'll notice in between that shaded region and the x-axis, there's blank space, and we said that was going to create the hole. So now I know I'm going to have two radii. I'm going to have my outer radii. I'm going to call that big R, right? And that's going to be defined by my very top function. So it's going to go from the very top all the way down to the axis that I'm revolving about. So it's going to go into what I colored purple all the way down to the red. So in this case, it's still going to be top minus bottom. My top, let's see, is going to be the square root of x minus 1. And my bottom, well, it's just the x-axis, so that's 0. So my top radius is the square root of x minus 1. Excuse me, my big radius. My little r now is between the lower boundary here and the x-axis. I know that's super hard to see. I don't know if zooming it maybe makes it a little better. So my little r is between the lower curve and my axis. Again, still top minus bottom. My top here is x minus 1 quantity squared. My bottom is still the x-axis, which is 0. So I have x minus 1 quantity squared. So now when I do my volume, I still have pi. My integral, well, my limits, it looks like I go from 1 to 2. Again, this is about the x-axis, so I have x values. So 1 to 2. I'm going to have my big R squared minus my little r squared, and that's going to be dx. So again, this is my big radius, is square root of x minus 1. My little r is going to be x minus 1 squared. And now I'm going to use my calculator to get the value of this integral. So let's see. Again, I highly recommend putting this into your own calculator so that you can see that your parentheses and everything is set up correctly. Let's see. Sorry about the delay here. Okay, and so when I do that, I get a volume of approximately 0.942. All right, I think that's enough for today. We'll look at the other examples tomorrow, so making sure that we understand it, and then looking at what happens when we revolve about something other than the x or the y axis. All right, see you tomorrow.